I don't think so. And I'm gonna blame another instructor, no names, but I took that problem from someone else.
That's what I did too. That's a tricky taught us to do it.
Oh, yeah, you did.
That's what I had to. That's where I got this. You can't do y over or x over y. You do y over x.
You can factor it. I'm just not sure what to do once you factor it. Have you done 3 yet? I've done 3. Y is negative.
There's no why.
Oh yeah. So I'm sure that that equals y prime, right? That makes sense, right? So it's y minus y squared.
Can you say?
No. Because you didn't change anything else now it's for
Right, so that's a y over x. No, I think I just transferred.
Did you do somewhere else?
No.
X equals y minus b y.
Is there an easy way to check the
Oh, you could,
Put it in your calculator and then watch your calculator.
all right, Flores, let's come
Yeah. Sometimes calculators fail.
Did 3 come up?
Whether or not I got the right y over because there's an x there. So you spread the x out. Yeah, so you spread the x out and you get y over x, which is what you want. Equals y over x. Right, and then you can flip it over. So then you flip it back over to this side and you get y over x plus y divided by y, and then you can split that apart and it becomes b. This becomes
All right. So, yeah, skip number 2, that will reduce your work anyway. Skip number 2, because I don't think that fits the form of a Bernoulli equation.
right, because you can just inverse it. So it's more of a b plus 1, which actually helps me because I.
So we're gonna move on, and I want to talk a little bit for the rest of the time about section 2.1.
Oh man, 2.1. Shit.
Population models. Okay.
I realized I was factoring.
So one thing, the question comes up: where do differential equations, where do they ever come up? Well, in analytical work in grad school, if you study math, differential equations are everywhere. But another common place is in growth models. And by population, it doesn't necessarily mean humans or animals, rabbits, anything like that. It could be population of cells. It could be population of what's that? It could be population of a rumor spreading. So in a population of people, the number of people who have heard a rumor, that could be the population. The population could also be radioactive materials. Okay? So population models have differential equations attached to them quite often. So a little bit, we talked about the water mixture. Tank of saltwater solution or brine solution, and we talked about. All right, guys, come on. Please, I don't want to talk over people. So yeah, we talked about the solution problem, brine solution with water coming in, water going out, and talking about the relative rates. That is receiving brine and going out. So if X represented the total mass or amount of salt in the solution at any time, it was modeled simply by rate in minus rate out. Okay? And then we had to figure those ones in. Water was coming in, or the solution was coming in at a certain rate with a certain concentration. The mixed up solution was leaving at a certain rate at some sort of variable concentration. Now, if we talk about a population model, and there are several, but population can be thought of similarly. A little morbid, but instead of rate in, we're talking about birth rate or something. Rate out, people leaving the population, okay? Whatever these individuals are, cells or people or whatever. Okay? So among other things, a simple population would have to take into account birth rate. We'll call that beta of t as a rate. And usually this would be measured in per unit of population, so per individual, per time. Population per unit time. So it could be per person per year. So oftentimes they talk about a birth rate as some sort of, birth rate is 0.08 births per person per year, something like that. Okay? And also the death rate, so the rate in and the rate out. We got births, we got deaths. And we'll call that S of t, curly S or something. It was supposed to be an S, it ended up curly. And that's going to be the same thing. So death, the mortality rate, number of people per population per unit time.
What about immigration and immigrant?
Oh yeah, we're ignoring that. So in a closed population, okay? So you can't enter from the outside already alive, and you can't leave alive. Okay, so we will ignore this is, and that simplifies things, of course.
Wait, immigration, you said?
Immigration. So think of this as some isolated population, like on an island before there were ships to transport different organisms all over the place, right? So on islands, there was no getting off, there was no getting on until ships were formed and ships were built and people could come and transport their organisms to this island, stuff like that. You hear a lot about non-native species and stuff like that. Well, on islands, you don't have that mixture with the outer world. Okay, so you get a different sort of it's a closed system. All right, so we can think of the population, rate of change of this population, dp dt, just like we talked about the rate in. There's a certain amount of solution per minute times the concentration. So we let P represent the population at any time t, and it's a birth rate times the number of people there. So a birth rate means nothing. It's per person per unit time. But I need to know how big the population is to know how many people are being born. So birth rate times the size of the population, that's the rate in, and the rate out, death rate, per person per unit time times the population. Okay? So if I factor out that P of t, we got beta t minus the death rate S of t all times P of t. Okay? So yeah, we're ignoring immigration. This is just a closed population of organisms or people or whatever. All right, so in the case, if we assumed one thing, we're not always going to assume it, but in the case where the birth rate and death rate are constant, so if you can count on that birth and death rate being constant, and call them beta naught and S naught. So if those are constant, then we get if those are constant, don't change over time, then dp dt is going to be, that's a beta naught minus S naught times the population, yeah? If I leave off the function notation. And this would be equal to K times P, okay? This is one basic model of growth rate. And returning back, if you were in Calc 3 here, this is something that we're returning back to into the intro to differential equations. This says, okay, under those conditions, if the birth and death rate are the same, then the time rate of change of the population is proportional to the current population. In other words, the larger the population, and K is a constant, right? It just represents beta naught minus K naught. Minus S naught, sorry. Then it says that the rate of change of population, so the growth rate, is proportional to the current population. This is called the law of natural growth. Okay? And it's separable. So, let's mark that. This also happens to be a nice separable equation, which we love. Okay. So, what would the solution look like? Well, let's separate it. But we get dP over P equals K dt, yeah? Okay. And that gives us natural log P equals, I integrated, didn't tell you, but integrated. Gives us natural log P equals KT plus some constant of integration. Now, tell me about this. If this represents an actual population, whether it's people, organisms, bacteria, whatever, we can assume one thing about P is that it's positive, yeah, non-negative. Okay, if P is 0, that doesn't exist. And if P is 0 here, then what does that tell you about the rate of change of population?
Nothing. Well, it's standstill or nothing.
Standstill. If the population were 0, then dP dt equals 0. No change in the population, which makes sense, right? If the population of something ever hits 0, then it flatlines. There's nothing to nobody to repopulate, nobody to die. Yeah. If there's one person left, it depends on if you depends on if you believe in the literal interpretation of the Bible.
That's a good question.
God can take a rib and create something up, or create a woman again. Okay. All right, sorry, I don't want to go there. That's a hot topic. All right. So we get if you apply the exponential function to both sides, then assume P is greater than 0, so then I can just abandon the absolute values. We get P equals e to the kt plus, well, times e to the c, and I'm just going to call that
G.
A or something.
Q. Psi.
Where A is a positive constant. Now K could be positive or negative, we don't know. So we get this is called the law of natural growth. And it's exponential, right? Okay, if K is greater than 0, then it says that as long as the population is positive, the growth rate is positive, yeah? Okay, so if that's the case, if K is greater than 0, the larger the population is, the faster it's growing, the larger its growth rate. So what does that look like? Oh, yeah, it's exponential. And in fact, that A is, oops, a little bit more. If we take P of 0, we get A times e to the 0, and that's our initial population. So I can just say A, okay, that coefficient or that coefficient in front represents the population at time 0, so we can call it P naught. Therefore, the total model for this would be P naught e to the kt. And if we graph that, there's P naught, and it says if K is positive, we get unchecked growth. Yeah? Okay.
Yeah. Like enough data is
What, is this enough to find a population, say like 500 or 600 years ago?
Well, oh, if it followed, this is a very strict model, right? So it results in unchecked growth if K is positive, which for most populations is not realistic, especially over a long period of time. So it's a simplistic model. That's when we took, you know, the birth and death rate to be the same. Oh, by the way, K, go even further. Remember, we said K was birth rate minus death rate. Okay, that's what we call it. All right. So one thing to notice, this is if K is greater than 0, right? So let's do a little examination. If the birth rate is greater than the death rate, in other words, if beta naught is greater than S naught, then what can you say about that constant up there, K? Right. It's greater than 0. And we got e to the positive kt. Okay? And that's what happens if that constant k is greater than 0, then we get population is increasing. Yeah. In fact, it's increasing unbounded over time. So that might not be very realistic. Now, on the other hand, what if the birth and death rate are identical? Right. We can even check it in this equation. If the birth and death rate are the same, if they're equal to each other, then that constant k is 0. And e to the 0 is just 1, and the population is constant at p. Okay, so like I said, like we talked about the second day, a population model, and this is a simplistic one, but it should obey some of these basic requirements, right? That makes sense. If the birth rate is larger than the death rate, then our population is going to be increasing, okay? If they're the same, every birth replaces one death in the population, then the population would remain constant. And the final case, if the birth rate is lower than the death rate, what can you say? Right. And does the equation bear that out? If S naught, if the death rate is greater than this, then that constant is negative. And P of T would be decreasing, because it would start off at P naught and decrease. Exponentially. Okay? All right, so next time we're going to do a little bit more and not assume anything about that birth rate and death rate, and we're going to look at, well, how it results in a specific equation called the logistic equation. Okay? So, next time, I'll write it down. Just write that part down. All right, we won't make the assumption that it's constant, the birth rate is constant. And we'll look at what results. So, and hopefully put something together as far as the solution of this equation and some slope fields as soon as we get some things cleared up with this computer. Okay? All right, so for next time, over the weekend, I know. I'm going to be here at Math Fest all day Saturday. I got to be here at 7 a.m., 7:30 a.m.
Is that voluntary?
for Math Fest. gonna be a bunch of junior high and high school kids. That's how awesome.
Is it volunteer?
But I got to, my contribution was I got to write the statewide portion of the calculus part. So we got most of the problems. So that'll be fun. Maybe I'll be trying to get a copy of it. All right, so for next time, what we're doing, I got a couple things to pass back to you. Oh, I didn't write this down. So it's going to be section 1.6 homework problems. And I do have a homework sheet for you. Finally, I got a list. And I want you to read section 2.1. Okay, and we'll pick up there next time. Okay, two things before you go out the door. Problem set. 4 problems. That's it. 4 problems. And these are the ones that are due. That's 2 of them. These are due next Thursday. 1 week.
Nice. Odd problems.
And I have a homework list. But, so part of the reason I was giving you problems day to day was because I was trying to vet all those problems before I assigned them. Okay, but I've given up on that. And so I got this homework set from someone else. So the only caveat is if we skip a section, I'll make any announcements if we have to skip a section, or I may delete problems. Delete. Rarely will I add problems, but these are for nightly practice problems. The problem sets now you guys know are the ones that I collect next Thursday, okay?